Okay, let's get started. Cool. This is the second lecture, and you guys aren't scared yet, so we can continue. We'll basically continue what we've... Oh, this doesn't look right. This is spring 2013, right? Let's do this. This looks... You and I haven't adjusted to the new year yet. Okay, we'll talk about fundamental concepts in ISA. But before that, Rachada's office hours this week have changed. He's going to be available today, 4:30 to 5:30 p.m., and Sunday, 4:30 to 5:30 p.m. So make a note of this. And this will be an announcement on the website, right, Rachada? Where are you sitting? Oh, OK. You're far away from the camera. OK. This is the agenda for today. We're going to finish up logistics from last lecture that we started. And we're going to talk about why study computer architecture. Hopefully you guys have your own reasons, but I have my own reasons. It's an exciting time to do that today, as opposed to 20 years from now, 20 years from in the past. And we'll talk about some fundamental concepts, and we're going to dive into ISA basics, instruction set architecture basics. If you need a chair, there's a chair here.
Awesome.
There you go. And this is a big sofa. OK. So I'll go over some review slides just to brush up your memory from last time. Remember, we covered the levels of transformation. There was a reason for this. This was abstraction, right? Such that people who are writing stuff over here do not need to know how the logic operates. We built up these abstraction layers. But then we decided to break those abstraction layers. We want to cross those layers in this course, right? To understand what's going on underneath, as well as to understand what you do over here affects what happens up here. And the reading that I assigned to you last time, how many of you have read it? Good. That's a good fraction, actually. Well, all of you should read it. But it talks about the transformation layers and also other things that we're going to cover today. But this is the focus of this course over here. But I also want to show this to you. Today, most computers are user-centric. So in the future, when we're designing computers, it's good to think about the user. For example, some decisions that you make below over here may be optimized for maximum performance, but that may not be what the user wants, right? Maybe the user really cares about one program that's really important. And if the microarchitecture you're designing is not giving the right knobs such that that program gets its performance, then maybe you're not designing a good computer, right? That's why I like putting the user into the picture. Whenever we design computers, we should really be thinking about the users themselves. So maybe user-aware microarchitectures are interesting, right? If the user doesn't care about high performance, maybe you should be optimizing for energy. A lot of the mobile phones today try to do that, but still they're not good at, they're not optimal at doing this. So keep this in mind. Basically, the entire stack perhaps should be optimized for whoever is using the computer. And the user changes also, right? Whenever I use my cell phone, it's different from the patterns you use your cell phone. Perhaps the computer should adapt to the different usage patterns. Today, there are things in the operating system that are trying to do that. For example, there are machine learning algorithms employed in some of the operating systems, Windows, that try to figure out what when you're going to check your email, for example, and that try to prefetch some of the programs or the emails that you're going to if it detects that you're going to actually check your email at 9 a.m. in the morning. Right? There are algorithms that do that. So that's one example. But hardware is less so optimized for the user because it's a little bit far away. But there's no reason to not provide the knobs. OK, what will you learn in this course? We haven't covered this. I rushed through this last time. So I'll briefly talk about this. Basically, we'll learn about fundamental principles and trade-offs in designing the hardware and software interface. And major components of a modern programmable microprocessor. Our focus will mainly be on a programmable general-purpose microprocessor, but I'll give you examples from more specialized microarchitectures as well, and architectures as well. And how to design, implement, and evaluate a functional modern processor, something that works, basically. Hopefully you're all here for this. It's fun, right? Building things. And my focus will be on actually two things, not only fundamentals, but also the state of the art. And I'll also talk about recent research and trends, because computer architecture is a fast-changing field right now. And last time I talked about two things to you. Memory performance attacks, remember? One program was denying service to the other one. This is a new research issue, actually. And the other one was DRAM refresh. In traditional computer architecture courses, you wouldn't even talk about DRAM in general, but you'll learn about DRAM in this course. So the focus will be on recent research as well as state-of-the-art, because you'll be building the machines of the future, right? Or you'll be programming the machines of the future, depending on what you do. Or maybe you'll be making the big bucks and figuring out what the machines of the future, what market the machines of the future should go into, right? Depends on what you want to do. If you have the right mindset, you'll get the right things out of this course, and hopefully it'll be useful 20, 30 years down the street. Okay, and in the labs, you'll design a functional modern processor. The labs actually will be a combination of RTL implementation and higher level simulation so that you get exposed to both aspects of computer architecture. Initially, we'll start with RTL labs where you'll implement an ARM core, a toned down ARM core, and then we will do C-level simulation to see how you can actually make higher level design decisions. And this is how actually computers are designed today. Normally, for example, a company like Intel or AMD or Oracle, whoever designed microprocessor chips, they do high-level simulation first to figure out what kind of things should be put into the processor, what kind of algorithms should be employed. Should we employ out-of-order execution or in-order execution, for example? Those decisions are made at the higher-level simulation. Because if you want to make that, if you actually implement in RTL all of those different types of processors, it's a way time-consuming process. And in fact, you cannot even simulate fast in RTL. If you want to simulate a long workload, for example, a database transaction even, it takes very long to simulate at RTL level because you simulate every gate in that case, right? Every wire. Whereas higher level simulation, you abstract away the gates and wires. You just model the functionality and timing of those. And you can do you can make much faster design trade-offs with higher level simulation. That's why I want to give you the both perspectives as a computer architect, as a designer. And you'll do different trade-offs at different levels. So it should be fun, actually. But the first labs will really start with RTL because that's something you really need to know. A higher level simulation, it's easy to cheat in higher level simulation. It's easy to say that this takes 5 cycles, right? But it may actually take 50 cycles. If you make that decision wrong, then you have a problem, right? You may design a processor that doesn't work too well. And there have been examples of this when we get to some cases. I'll discuss that. But that's why we want to ground you first with the RTL implementation, because you're really building a gate-level model when you do implement something in RTL. And when you go to the higher level simulation, it's important to know how things should be implemented in RTL. Maybe you don't implement them in RTL, but you have a good idea of, oh, this multiplier is probably going to take 5 cycles at this frequency, right? Maybe it'll take 6 cycles, but then higher level simulation is flexible, right? You don't simulate one value. You say, this multiplier may take anywhere between 3 to 10 cycles. Let me vary that and see the effect on the workload. So that way you can make good design decisions. And maybe you design a multiplier that actually fits for your workload that way. Okay, so focus will be on functionality in the labs. You should get the labs correct. But there will be components of the labs on how to do even better. So we'll ask you to do extra credit assignments if you wish to do that to improve the performance of the thing you designed. I guess the last thing, which is also very important, which applies to anything in life, not really just this course, you'll learn how to dig out information, think critically and broadly. We talked about that in the last lecture, so I'm not going to harp on this again. And how to work even harder, I guess. This is going to take time, because all of this, especially the labs, will take a lot of time. But you may have heard that exams and homeworks actually do take a lot of time, too. But it should be fun. So what are the goals? There are 2 goals. I briefly talked about this earlier, but I'd like to familiarize you, at least those of you who are interested in computer system design, you should all be if you're here, with both fundamental operation principles and design trade-offs of processor, memory, and platform architectures in today's systems. Again, fundamentals and design trade-offs are important. A lot of things I'll describe will be in terms of trade-offs, because every decision you make is a trade-off. There's no perfect decision. Actually, this is probably true of the entire world, right? There's nothing really perfect, if you will. Everything's a trade-off, and there's a positive and a negative. And it's important to know what the positives are, what the negatives are, and pick the design decisions that actually fit with your design point, as we will see. If you read Pat's paper, design point, you know what I mean by a design point, right? We'll get to that. The second goal is to provide you with the necessary background and experience at least initial experience, to design, implement, and evaluate a modern processor by performing hands-on RTL and C-level implementation. Again, the emphasis will be on functionality and hands-on design. That's why I'd like to have you do the assignments individually, because individually you'll learn a lot more, a whole lot more than you would have learned with a group. Now, real teams operate together, right, today, because no one can design a processor that's complex as we do today, but your design will be simple. It won't be a complex processor. Besides, you'll get a lot of chances to actually work in teams in real life later on. Okay. I've talked about this last time, but I'll emphasize it again. This is classified under computer hardware, but it's really a hardware-software interface course. And you will be much more capable if you know both the hardware and the software. So keep this in mind throughout the rest of the course. Okay, required background, I think you all know this, right? You need to know 240, you need to know 213. I should have taken this out, given that no one has taken 243. These are some of the things I expect. Definitely learn the material thoroughly. Attend the lectures. Lectures are not required attendance, but if you attend them, you'll do much better. Do the readings, do the homeworks. Work hard. But you're at CMU, so you must be working hard. Definitely ask questions. If you have concerns about something, ask questions. Take notes and participate. Perform the assigned readings. This is important. I'll actually get back to that when we talk about readings. Come to class on time. I think this is important. We'll be posting, hopefully, the videos online, but there's a time delay. For example, the video from last time is not posted. I assume it'll be available soon, right? But whenever it's available, we'll post it. But I think you'll learn a lot more in class than on videos. Actually, you could have watched the videos from spring 2013. How many of you have done? No, not all of them. There are too many. Things I describe will be different. I'll adapt. Again, this is a dynamic environment, right? I'll adapt to dynamic events. Okay, this is very important, actually. This should have been bold, perhaps, instead of come to class on time. Start early. Do not procrastinate, because this will bite you if you procrastinate. Again, there are 7 homeworks, 7 lab assignments. We will have some slack. There are some late days that are allowed, but if things pile up, tough. And if you want feedback, definitely come to office hours. We have 4 TAs. I think a total of maybe 15 hours per week, office hours, maybe 10 hours per week. So definitely come to the office hours or scheduled meetings. This is important. Okay, and always remember this. This is one of my favorite quotes by Louis Pasteur, who invented pasteurization. You know about pasteurization process? Milk. You can drink milk because of that today, right? Well, chance favors a prepared mind. And this is him. Basically, I like this quote because people think that you're lucky, right, in some cases. But you actually create the opportunities to be lucky in general. One of my favorite examples is from research, for example. If you actually are doing research, you may be lucky to stumble upon a problem. People may consider you lucky to find a really good problem to solve in research. But that usually comes from preparation, right? If you're prepared, if you know, for example, what we discussed last time, if you actually knew that DRAM operated in one way, you could find the problems associated with it and decide to do refresh in a totally different way. Right? You could think that you're lucky that you found that idea, but if you didn't know, if you hadn't prepared 10 years ago and figured out that DRAM operated this way, then you wouldn't have been lucky. So it's really the prepared mind that becomes favored by chance. So your luck really is built by you, if you will. Now that's not always true, obviously. There are events that are just pure chance, but you can bias your coin by preparing well. Okay, well, I guess we talked about this. How you prepare and manage your time is very important, and I've talked about this too. It'll be a heavy course, but you'll learn about a lot of fascinating topics that are of utmost relevance to industry today. Not only the hardware industry, again, the software industry also. Because, for example, Google and Facebook have data centers today, and a lot of their these data centers consume a lot of power, and they actually affect pretty much the entire software stack that is running on them. Right? And the design decisions that you make at the computer architecture level, how you design the memory, how you make it reliable, actually affect the bottom line operation of all those data centers. And they actually are, or maybe thinking of, designing their own platforms, their specialized architecture for their workloads, or maybe semi-specialized architectures. So whatever you learn will be applicable to pretty much anything in industry. And if you want to go to academia, academia too. So these are actually very, for me, very fascinating topics. I hope you will find that they're fascinating to you too. Okay, I think we've covered this, so I'll just skip this, but I'll remind you that there are 2 homeworks due. One is due next Wednesday, January 22nd. This is the homework where we will get to learn about you. How many people completed this? Okay, great. That's a good start. I'd like to see more hands next time. And the hand-in folder is ready. There was an issue with that. I think it's gone now, since you've completed it. Right. Okay. Homework 1 is due next Wednesday, January 29th. And this will be synergistic with the Lab 1, although homework 1 is due a little bit later. And Lab 1, just as a reminder, it's a functional C-level simulator for a subset of the ARM ISA. And it will be due next Friday, at the end of the Friday recitation session. Actually, homework 1 is already posted. We'll post Lab 1 later today so that you can get started on it right away. And remember that homework 1 and Lab 1 are synergistic. We'll try to do that as much as possible throughout the course. It won't be possible in some cases because labs require implementation, whereas course is more conceptual, right? It's very hard to synchronize the material in the labs and the course. Yes?
Are assignments generally due before class or before midnight?
Oh, that's a good question, actually. What did I say over here? Nothing. So for the homeworks, I'll say before midnight. Whenever it's before class, I'll tell you. For the labs, it will be the end of the recitation session on Friday. Labs will be always due on Friday. Okay, some readings for this week. You already know that. Actually, some of you have already done this reading. There's also this reading that I assigned. How many of you have done it? Yep. So-so. So maybe 6.5 people. That's not bad. Yeah, I'd like you to do it. All of the readings actually are a fair game for the exams too. In this course, I won't be assigning a whole lot of readings that are advanced like this. But I think this is important for you to read. If you really want to do a lot of reading, take 740 if you survive this class. Hopefully you will. Hopefully you will. Okay, but there are also some fundamental readings. One is Pat and Patel book, Chapter 1. Actually, we should have these books in the library. Rachada, I cannot find you there. Okay, there you go. You're at the very end. My eyes are getting worse, I guess. Yeah, we should put the books in at the library so that people can borrow. I have copies of these. Oh, we may have them online also, actually. Yeah. Okay, but this is the fundamentals chapter, and this is a good book that talks about computer systems. And the Patterson-Hennessy chapter 1 and 2, Introduction, Abstractions, ISA. One chapter talks about MIPS. We're transitioning the labs to ARM this time, which is a much more common ISA. So you don't have to go into the details of MIPS, but it's good to look at the Introduction, Abstraction as an ISA. And there's a reference material throughout the course. This is on the course website. You can find the ARM reference manual. Actually, one of the best places you can learn about processors is the reference manuals for different ISAs. These tell you a lot of information. You need to decode it a little bit, but for example, the x86 reference manual is about maybe 2,000 pages long. So this is your assignment for this week, 2,000 pages. I'm just kidding. I'm just kidding. It's not for this week, but this is throughout the course. I've learned a lot by reading the x86 reference manual once in a while. We won't be doing x86 in this course, but I'll be, especially when we cover the ISA, I'll show you some examples of x86 ISA, how complicated it is, and what kind of design trade-offs they made. Some optional and mentioned readings. I'll mention a lot of readings in the course, and they will be placed on the course website. Actually, let's take a look at it quickly. They won't be required, but if you're really interested, these are actually are good material for you to take a look. So if you go to lecture schedule, yeah, you can see that there are some optional readings that I've talked about if you're interested, you can go and look at it. Especially when you're listening to the lecture, you can take notes for interesting readings. For example, yeah, the Rader paper over here that we've discussed, retention over DRAM refresh. If you want to learn about a concept that you're interested in, you can go and do that reading. Or come and talk with us. So this is how you can actually enhance your learning in this course. But this is not required. So if you have to choose between doing your lab and doing the reading, choose the lab. Okay, a note on books. We don't have any books that are required. And I'll assign readings from some books and we'll make them available. But hopefully you'll be resourceful enough in finding and doing the readings. The material will be contained, and actually pretty much all the material is in the last semester's, not last semester, spring 2013's class. You can find pretty much anything over there. Okay. Any questions? I've gone through logistics really quickly, yes?
On the website, I believe it listed those required papers and made it seem like you wanted them all read by today, but you just said in the slides like that was for the week.
Oh, that's right.
Are there going to be more readings from Friday, or when you list the stuff on Wednesday, is that just be the entire week?
Yeah, it's for the entire week. It's a loose concept. Yeah, if you read them earlier, the earlier you read them, the better. But if you read them by the end of the week, that's also fine.
And also, I'm not sure how much you could answer this, but I know you said everything in papers is fair game, but obviously, like the one paper you had was like pretty thick on stuff.
That's right.
What exactly do you mean by fair game?
Oh.
That's I'm assuming not everything's covered.
Sure, that's a good question actually. I'm not going to ask you in this paper what percentage performance improvement did we get with this mechanism. That's not good. That's not. But I'll test you on the concepts, for example. For example, what is a memory performance log? Why does it happen? What are the causes of unfairness in a memory controller? Right. And I've actually described that in lecture also.
Yeah, I just mean like in your paper, it was like talking a little bit about like merge buffers and stuff, and I was like looking at it, and I was like, I don't think we're covered.
Yeah, exactly. Don't worry about those details. Think more about the concepts and trade-offs. So a good way to gauge is to look at past exams. Okay. But I'll test you. What I'm really interested in is whether you have learned the concepts, trade-offs, and the fundamental structures, not the details. We'll talk about, maybe we'll get to, not the merge buffers, but missed status handling registers later on in the course. But if it's in a reading, and if the reading introduces a concept and I don't introduce the concept in class, then it's good for you to learn, but you'll not be tested on it. Okay? Yes?
For the P and P reading, you said just try to get a hold of it somehow.
That's right, yes, Pat and Patel. It will be, actually we may have it, so we'll be in touch with that. I think do we have it?
We have some chapters posted online, and if you look at Spring 2013, there's also some chapters available. I think you only require chapter that we do not have in chapter 2.
Yeah, that could be true actually. So let's take a look. Yeah, let's put it on Spring 2014 also. Here you go, Pat and Patel, Chapter 4 is there. I don't know why Chapter 1 is not there, but is it up there? Lecture 2. Oh, there you go, yeah. So you can actually access it even right now if you go to Spring 2013 website. But we'll put it on Spring 2014 as well. Oh, that's right, yeah. So we will put that on the reference desk at the library. Okay? Engineering library, yes. The one in Wien Hall, right? Yes. Actually, it may still be there. You might want to check. Because it's a popular book, you might want to check that whether the book is in the library. But we'll definitely put it on the reference desk. Okay, these are good questions before we jump into why study computer architecture. Anything? Just trying to make sure if I have the time here. Did I put my cell phone somewhere here? Okay, I just want, what is the time? 1 o'clock, okay. I don't know where I put it, but I hope I didn't lose it. Okay, it's here. It's a lot easier for me to check this then. Okay, so why study computer architecture? Well, we've covered what first of all, what is computer architecture, right? This was my definition from the syllabus. It's a science and art, and perhaps more of an art, of designing, selecting, interconnecting hardware components and designing the hardware-software interface to create a computing system that meets some goals. And we'll soon distinguish between the terms architecture and microarchitecture, and we have a little bit last time, but this covers pretty much architecture and microarchitecture, both, right? So why study this? Well, first of all, it's exciting, I think. You design new things, right? You enable new things. But one of the things that has driven, why study it today? Right? People have been studying it for 50, 60 years. Isn't it all done? Haven't people all invented all kinds of architectures by now? Actually, believe it or not, some people have argued that in early 1980s, you should not be researching computer architecture anymore because we've hit the best possible designs that we could potentially hit. MIPS R2000. And obviously it's not true, right? We've been inventing much better architectures because you could do much more, right? You're really inventing new things and improving the system design. It's not clear when it will end because it's really based on your creativity and based on what you can do and based on the trade-offs that you make. So why study it today? Well, what has driven a lot of the improvements is what is called Moore's Law. How many of you have seen this before? Okay, good. It's not really a law, it's just an observation, right? It's a curve fitting that Moore did in 1965. Basically what he did was he looked at the number of transistors. Actually, it's even before this. He looked at the number of transistors, number of devices that you can put on a chip, right? And he plotted that, and he figured out that the component counts double every other year. At that time, it was every other year or so. Now there are arguments that it doubles every 18 months or so, right? Basically, the transistor count is doubling every 18 months or so. And this is enabling things to do with those transistors, right? And you can read Moore's paper. I'm not going to assign this as an optional reading, but it's only a 3-page paper. That's relatively easy to read. But that's the takeaway. This is the years on the x-axis, transistors on the y-axis. Transistor count is increasing exponentially over time. So this begs the question, what do we do with these transistors? And this is another way of looking at it. This is actually a newer chart. This is Intel's chart from 2005. This is from Wikipedia's chart, I believe, for different kind of processors also. It's not only, it is Intel processors. Yeah, it is Intel and AMD processors. It's x86 processors. Yeah, the transistor count is doubling every 2 years, according to this. So what do you do with that? Well, hopefully your readings this time should give you a good idea, right? You could design many different things. You could design a better memory controller, for example, by burning more transistors. So I'd like to take a look at that. But you could do other things with that also. Although this actually doesn't presume that your transistor count should be doubling. Even if your transistor count remains the same, you should be able to do all of these. But these become easier, much easier, if you have more computing power at hand on a chip. So let's take a look at that. What are the things that computer architecture enables? And as a computer architect, hopefully you will enable in the future. First, you can enable better systems, right? You can make computers faster, cheaper, smaller, more reliable, ... Whatever is needed for the user, whatever is needed for the problem at hand. By exploiting advanced and change in the underlying technology and circuits. And by exploiting your creativity, maybe you organize things better, right? And we'll see that, right? We'll see techniques like out-of-order execution, for example, improve performance significantly compared to in-order execution. I mentioned MIPS R2000. MIPS R2000 was a processor that was very simple at the time, and people argue that that's a great processor. But people have improved upon that by making computers faster than that. MIPS R10000, for example, employed out-of-order execution. That was in 1996 or so, or 1995. MIPS R2000 was around 1980s, early 1980s. So basically, it's computer architects that enabled this. You can enable new applications, right? If you actually take advantage of the new technology, you can think of new applications that didn't exist before. For example, 20 years ago, could we do lifelike 3D visualization? Not that I know of, at least. Maybe supercomputers tried to do that, but that was extremely expensive. Right? Today, you could almost do it on your cell phones. Can you? Pretty much, right? You have graphics engines on your cell phones. Maybe you burn a lot of battery quickly, but it's very good. I mean, maybe it's still not perfect. Like, we don't have virtual reality yet, but it's pretty good. And hopefully we'll have virtual reality at some point too. Personal genomics is another application that people are trying to enable. Right? Can you actually sequence your DNA and analyze it very, very quickly, almost on the spot, such that the doctor can make a decision very quickly, maybe a life-critical decision. Right? And this is just one example. Right? It's not only personal genomics, but it's also out of all of the health data that we've completed, that we have collected over many, many years and over many, many people. Can you mine that data quickly such that the doctors can make much better recommendations for a drug, for example? It's a tough problem. It's what's called a big data problem, if you will. You have huge data sets, and you need to analyze those data sets to make some decisions. How do you enable that? Well, you need faster, more efficient, cheaper computers. If you want to enable this in an embedded manner, then you want it to be even smaller as well. You want it to be extremely low power. So these new applications, you can imagine, you can actually increase this list. I'm not going to go over that. You can think of, and it's a good exercise actually, because you may actually come up with a new company idea if you think of new applications. Right? A lot of the companies that have been successful came up with new applications, and even if it's just for fun, you can think of new applications. But this has all been enabled by new architectures. Better architectures. You can enable better solutions to problems. Even if you're not enabling new applications, you can have better, more featureful software. So software innovation has been built into trends and changes in computer architecture. At least until the last few years or so, there has been 50% performance improvement per year in computer performance. And that has enabled richer software that we have today. If that performance improvement was not there, you wouldn't get the features that you would get on any of the systems that you have today. And I guess why study computer architecture? The first thing is understand why computers work the way they do. This is just out of curiosity, so that you can achieve all of these things. If you don't understand how they work the way they do, probably you cannot fix these problems. There may be other reasons, by the way, but these are my reasons that are interesting. Okay, so we've been doing that for a long time, but why is today an even more exciting time to study computer architecture? I'll give you my perspective, but this is pretty much true across the industry. Industry today is in a large paradigm shift. Single-core processors which execute a single thread faster and faster, the performance improvement has pretty much dropped off with single-core processors because it's become much more difficult to improve that performance. And we'll see the reasons for that. Because it becomes a lot more complex to extract performance out of a single thread. And because the architects couldn't find out better ways to improve the performance of single threads, now they're designing processors that can execute multiple threads, multi-core processors. Instead of having a single core, actually let's do it this way. Instead of having a single large core, which is difficult to design and maybe power hungry, you have many small cores. Maybe not this many. But there are actually designs that are this many that we will look into later on. You have a multi-core processor. And this is a large paradigm shift that has happened in the recent years. And this actually enabled many different potential system designs, because this is really not a good shift necessarily, right? Because you could actually reduce performance. Now, the companies that really care about performance try to not reduce performance. So Intel, for example, when they took their large core designs and when they designed multi-core processors, they really didn't split up the large core. They didn't try to make it smaller. They tried to not lose performance on the large core. Because if you actually lose performance when you go from here to here, then you're actually making some existing software much slower, right? And no one wants that. Because some other company can actually design a processor that's faster now, and you're out of the market, pretty much. Okay, but basically, it's not clear how we'll grow the system going into the future. This is not necessarily a good choice, but this was a necessary choice. This was the only choice that industry had. Well, it wasn't the only choice, but this was the only viable choice, I should say. So there are many different potential system designs possible, such that you can go to a much better system than today. And there are many difficult problems that are caused by this shift, or that are motivating this kind of shift. One of the reasons why the industry went from a large core to multi-core, improving the performance of a single core to multi-core, to designing multi-cores, is power was a problem. Right? It's much harder to power a much larger core because it's much more complex. The complexity of design was a problem. It became very difficult to design a large core that extracts high performance. We'll see out-of-order execution, for example. One of the techniques to get high performance out of a single thread is to execute its instructions out of order instead of executing them in order, in program order. And this takes a lot of circuitry, as we will see in one of the lectures later on. Why? Because now the hardware needs to find which instructions are independent of each other and and it needs to execute them concurrently. And the circuitry is hard to do because you need to keep track of dependencies between instructions in hardware. And we will see that in one of the later lectures. If you don't know how this is done, we'll see that. And as you go into the future, to extract even more performance, you'd like to look at a much larger window of instructions to figure out what are the independent instructions. And that is expensive. Instead, it's much easier to say, oh, I'm going to execute instructions in order, but let the programmer figure out which instructions can be executed in parallel. Right? Now you punt the problem to the programmer. The programmer somehow programs in threads. Instructions still execute in parallel, but now it's the burden of the programmer to figure out which instructions execute in parallel, right? Not the hardware. So hardware is not complex if you go from here to here, but the programmer's life is much, much harder. That's the programmability wall problem over here. There are difficulties in technology scaling that has motivated this. Actually, there are other problems that are being motivated by this. Today, this is the processor-centric view of computer architecture. If you think about DRAM that we discussed in the previous lecture, DRAM technology is not scaling as well to smaller technology nodes. So refresh is becoming a big problem, for example. So that's another reason why it's a very exciting time to study computer architecture, because we're running into scaling issues as we scale the size of the technology. If the transistor is occupying only a few atoms in the future, how do you actually make it work? That's a reliability problem. How do you actually solve the refresh problem? That's also actually a reliability problem, right? Because the capacitor actually leaks. And you don't want it to leak. You want it to keep the charge. So these problems are actually coming from technology scaling. And today is a time technology scaling is actually affecting the design significantly. So all of these difficult problems are there today. That's why it's a very exciting time to study computer architecture. And we'll talk about memory a lot. One of the other trends in computer architecture has been that it has been easier to improve processor performance compared to memory performance, for the reasons we will discuss later on. As a result, memory has become very slow compared to the processor. Then how do you bridge this gap? When a processor accesses memory, it takes 1,000 cycles. It needs to wait. So how do you ensure that the processor does useful work during that time? We'll talk about that. Okay. So basically, there are no clear, definitive answers to these problems today. That's why industry has gone into a large paradigm shift, asking the question, what is the processor of the future? What is the memory of the future? What is the I/O subsystem of the future? And hopefully, by learning about a lot of these problems and the fundamentals, you can solve these problems. And these problems actually affect all parts of the computing stack if we do not change the way we design systems. So if actually, one example is this, right? Instead of having a large core, you have many, many cores. Now you need to design the entire algorithm, program, runtime system, and perhaps the ISA, such that you can support what's up there, such that you don't lose performance, right? you still get good performance. And there are no clear or definitive answers to these problems. So I think this is my last slide related to why it's more exciting to study computer architecture today. By the way, it was not always like this. The choices in around 1990s in computer architecture were more or less clear, in the sense that technology was scaling nicely. We didn't have issues with power. We didn't have issues with reliability. So we could keep building larger and larger cores. It's nice for the software also, because the software programmer doesn't need to care, right? They just write a single-thread program, they bloat memory, and they don't optimize their program, and they still get great performance, because underlying hardware can supply you with a much larger, much faster core. So it was a little bit 1990s were the time when computer architecture was not perhaps as exciting. It was still exciting to me, but it was not as exciting, not as potentially important. But today it's extremely important because this is not happening anymore. Okay, so hopefully you can actually revolutionize the way the computers are built if you understand both the hardware and software, if you understand all of these different trends, and change each accordingly. And one of the goals I have in this course, which is not stated previously, is hopefully to enable you to have the background such that you can invent new paradigms for computation, communication, and storage. We'll cover computation and communication and storage very quickly soon. I'll recommend one book over here. Has anyone read this? Yes, you have? Oh, cool. For a class or for fun?
For fun.
Is it?
Mine is philosophy, history, philosophy, science.
Mm-hmm. Okay. Oh, okay. Did you like it?
Yeah.
Yeah. It's a little bit hard to read at places, but yeah, it's a good book. So this is essentially a philosophy of science book, actually history also. Basically, it analyzes the scientific revolutions, how scientific revolutions have happened over a long time. And it has different examples. For example, Galileo's revolution, right? But basically, the way I look at it is today, computer architecture or computer system design is undergoing a revolution, if you will. And the book, Thomas Kuhn in his book, classifies science into three things, three phases, if you will. One is pre-paradigm science. There's no consensus in the field. Nobody knows what is the best way to do things. Well, today we're kind of here, right? Or maybe here, revolutionary science. The second is normal science. This is great. Everything is, this is stability period, basically. You have a dominant theory, and you use that to explain things. Basically, it's business as usual. If you see exceptions to this, you say, oh, this is an anomaly. Don't worry about it. So this was the state of the art, if you will, in 1990s in computer architecture. The dominant paradigm, design better single-core processors. Right. That's great. If you run into a little power problem, oh, it's an anomaly. Right. So solve it with some other way. Maybe add more cooling. Right. So that's actually how this is not science. This is engineering, really, right? Computer architecture is really engineering and art. But you can apply the analogy similarly. And revolutionary science is now if these anomalies increase, you have many anomalies such that you can no longer use the dominant theory to explain things. Now you go into revolutionary science. You re-examine all of those underlying assumptions. Oh, maybe it's not a good idea to do this business as usual anymore. Maybe there's something better. So you re-examine things, and you go into no clear consensus in the field, and then hopefully at some point you go into normal science again, assuming this Kuhn's theory is true. Kuhn's theory has been questioned for a long time also by others too, but I like looking at this because it kind of explains, it kind of meta-explains the state of computer architecture today. So we're in this revolutionary period, so any good computation model or memory model that you come up with today can actually affect the systems we design into the future. Because there's no business as usual as we know it today. Okay, but first, the key thing is really understanding the fundamentals. So let's start with that. Because you can change the world only if you understand it well enough, and only if you do not ignore it. You can come up with a great paradigm, but if it ignores most of the programmers in the world, good luck with that. And I'll give you some examples also of that. And I mean, this could be a paradigm that ignores most of the programs in the world, right? especially if you do not provide the right hooks and the right software infrastructure such that the programmer cannot take take advantage of it. Okay, so it's important to understand the past and present dominant paradigms and their advantages and shortcomings, like the trade-offs. And we'll talk a lot about these paradigms and advantages and shortcomings of all different design choices that we will examine. Okay, let's start with some fundamental concepts. I think I'll take a break in 13 minutes. Any questions so far? By the way, that's not a required book, but I'd strongly recommend it. Even if you read it after this course. Don't read it in place of doing your lab. And you may get a copy of it if you do well on the extra credit assignments. Then it'll be your burden to read it. Or sell it, I assume, right? That's I'm curious, do people read hard copy books here? How many of you read hard copy books? Don't be shy. I try to read hard copy books. Okay. How many of you don't at all read hard copy books? 0. How many of you prefer the modern books, like on your computer? Some. I would think more of you would prefer the iPad-like books or Kindle-like books. That's not true?
They have less sentimental value.
Oh, they have sentimental value?
Like the ones on the computer, they just have less sentimental
value. Oh, less sentimental value.
Actually hold it here.
Oh, I see. So you do actually care about the sentimental value of the book.
I mean, it's like a baby.
That's true, but it's harder to carry, right?
That's true.
Yeah. I can more easily read the hard copy books, but carrying is the hard part. Okay, good. Then you'll get a hard copy book. Just let me know. Okay, some fundamental concepts. Let's first start with what is a computer, right? We're trying to design a computer. We're trying to understand design choices of a computer. What is a computer? Well, at the high level, there are 3 key components that we'll cover all of them. Computation, communication, and storage. And memory is a form of storage. And this is one depiction of it. This is a simple depiction. You have some computing units, perhaps this should be units, and some communication units, and some memory and storage units that are interconnected with each other. Actually, communication units can be pretty much everywhere, right? And we'll talk about interconnects that connect the different units later on. And memory storage units consists of 2 components. Memory system is the working storage, and storage system is actually the persistent storage. And this is actually a good example of how the paradigm has changed today. This is how we think of memory and storage today, right? You have working memory, DRAM, and you have storage, SSDs or disks. But going into the future, even this assumption is questioned. That's some of the work that's going on in my group and some other groups are trying to merge these 2 things. Like, why do we have this huge distinction between memory and storage? Well, the reason is DRAM, or main memory, has been extremely fast, and disks have been extremely slow. So we've created these different abstractions. When you access memory, you do loads and stores, right? When you allocate an array in C, for example, you really do loads and stores. It's not persistent, right? It's really a volatile data structure. Whereas storage system, it's disks, right? You go through the file system abstraction, and you've done that in 213, right? And that takes a lot of time and energy to do that, because you cannot just put an array in disk and access that array in disk, right? Can you? Why would you want to? Well, what if you want to build a really reliable system? Because DRAM is not reliable, right? You lose data. This is persistent. So you may want to have an array over there such that when the computer crashes, you still have the data changes you make. So that's one reason, actually. But if it's really slow, yeah, you don't want to. I agree. If it takes, like, I don't know, milliseconds to access the array, then your program will run like a dog. So we have this different abstractions accessing memory and storage today. But now, technology is changing. DRAM is not scaling very well. And there are some emerging technologies, which we will talk about when we get to it, that seem to be similar to DRAM in terms of their characteristics. They're much faster than disks. They're a little bit slower than DRAM, but they're non-volatile. So they keep data. You know the difference between volatile and non-volatile memory, right? Volatile means you lose data if you don't keep it powered. Non-volatile means the data stays even if you turn off the power. So there are some technologies like phase change memory or spin transfer torque magnetic memory that can actually store data even if they're powered off. And they're almost as fast as DRAM. Like STT-MRAM, the magnetic memory, spin transfer torque memory, is almost as fast as DRAM for reads. It's a little bit slower than DRAM for writes. I'll write these down just if you're interested. You can take a look at them. But these technologies are being investigated very seriously. And some of them are actually on some cell phones. Like phase change memory is used in some cell phones as part of the storage system. And STT-MRAM is another one. Now these enable a new opportunity, right? You can have a fully non-volatile memory system. And then why have this distinction between memory and storage anymore? Have both of them in a single place and get rid of all of those file system abstractions such that you don't run like a dog. In fact, if you have the file system abstraction, if every time you need to access this really fast memory through the operating system and through the file system, you're really not utilizing the underlying hardware well. Because this is really fast. It takes 50 nanoseconds to access. Going through the file system takes milliseconds. It's okay if your disk takes milliseconds also, but it's not okay if your storage medium is only 50 nanoseconds. So that's why today this is another example of why it's very interesting to study architecture today, because you have these new technologies that can enable new trade-offs and new system designs. It's always good to think about, are we actually utilizing the technology that we have well or not? Okay. Anyway, that was a digression, but take a look at some of these things if you're interested. We'll hopefully have a lecture later on talking about these non-volatile technologies. So what is a computer? We will basically cover all three components. This is processing. Processing will consist of control, which is sequencing and the data path, and memory, and I/O. Storage is not depicted here, but it will be somewhere over here. Okay. So one thing we will assume for most of this course is the von Neumann model architecture. All of your labs will be based on this. This is also called stored program computer, instructions in memory. There are two key properties of this. Have you covered von Neumann model before? Yes, in 213? So what are the two key properties? That's a hard question if you covered it. I'm fine with one. If you give me one, I'll be happy. Yes? Okay. Yes, that's a good one. That's one. What is the second one?
I'm not really sure about this, but it could be that instructions are stored along with data.
Yeah, you got it right, actually. It's the stored program, basically. Program is stored in memory. It's not it's not generated, basically. It's stored somewhere. It's in stored storage. And yeah, that's one. There are two key properties. One is stored program, and the second one is the first thing you said, sequential instruction processing. Basically, stored program means instructions are stored in a linear memory array, and memory is unified between instructions and data. It's really, there's no distinction between instructions and data. The distinction is really how you interpret the stored value. The interpretation of the stored value depends on the control signals, and we will see that very, very clearly. I guess this begs the question, when is a value interpreted as an instruction? You access memory, and you get a value. When do you interpret it as an instruction versus data? How is that determined? Yes?
Well, can't you make the program counter point to something that isn't actually an instruction, but is data, and it just executes it as an instruction anyway?
That's right, absolutely. So what you're getting at is when at the time when the program counter points to it, then you interpret it as an instruction. Right? Basically at the fetch stage, if you will, of instruction processing cycle. We will cover the instruction processing cycle. At the fetch stage, we will see that the program counter points to some memory location in that linear array. At that point, the control signals are such that that location that's accessed in the memory array will be interpreted as instruction, as opposed to an operand. Right? So basically, the interpretation of the data is dependent on the control signals. And we will actually generate a lot of these control signals in your labs as well as part of the LC3B microcode that you will fill out. The second is perhaps the even more dominant part of von Neumann model is the sequential instruction processing, the notion of that program counter to begin with. Basically, the abstraction is that only one instruction is processed at a given time. It's fetched, executed, and completed, and we'll see the instruction cycle soon, at a time, before the next instruction started, and this instruction starts only after the previous instruction is completed. It's very sequential, right? So there's a program counter, more appropriately called the instruction pointer. It really points to an instruction, right? It doesn't count the program. I don't know what program counter means, but historically that's what has been said. It identifies the current instruction that's being processed, and that identifies the only instruction that's being processed in the von Neumann model. And it's advanced sequentially except for the control transfer instructions, right? Yeah, control transfer instructions also like branches or indirect branches or calls that transfer control to some other point in the program that change the instruction pointer. So this is the model. And this is the model that we're going to assume for most of the course, although we're going to cover a lot of different models too. But for your labs will assume this. Well, this is actually a nice model. I'll contrast this with a different model right now, but I'll give you first the reference. This is actually the paper that introduced this model in 1946, Burks, Goldstein, and von Neumann. It may be a difficult to read paper. It's a 50-page technical report. But a better version, chapter 4, which will be assigned reading next time, is the von Neumann model. And this clearly explains some of the concepts of the von Neumann model. But there are two things: stored program, sequential instruction processing. And this is what a von Neumann computer kind of looks like. Basically, you store the program in the memory unit, and you have this IP. In this case, I say IP, instruction pointer, or PC. And basically, the control unit accesses the memory to get the instruction, and then processing unit processes the instruction. And then you have input-output machines. And we're going to assume a machine like this. Now, this is not the only model. Actually, there have been many, many models. So to broaden your perspective, I think I'd like to cover one model. Because going forward, this may not be the best model. Even though this is the model that we're going to examine and improve. Maybe there are some other models that we should examine, given that it's not doing too well. Right? So this is an abstraction to the programmer. The other one is, well, it's the data flow model. How many of you know the data flow model? No? Don't be afraid that I'm going to ask you, what is the data flow model? It's over here. OK. Basically, this is in complete contrast to the von Neumann model. In von Neumann model, an instruction is fetched and executed in the control flow order, right? Sequential order. And you can change the control with control flow instructions. In the data flow model, there is no control. There is no control flow. An instruction is fetched and executed in data flow order. Whenever the data arrives for that instruction, the instruction is fetched and executed. It's completely different. So here, the control flow is specified by the instruction pointer, and it's sequential unless explicit control flow instruction modifies it. Right? Whereas in the data flow model, an instruction executes when its operands are ready, not when the instruction pointer comes and says, instruction, you should execute now. Right? In other words, there is no instruction pointer. Right? The program counter is gone. Now, this could be a way to build computers. In fact, people have studied building such computers starting from the 1970s until the early 1990s or so, when this model became dominant in terms of performance. Well, but these are actually higher level models exposed to the programmer. But let me actually cover data flow model first. In this case, instruction ordering is specified by data flow dependence. Each instruction specifies which other instruction should receive the result. Right? There's no instruction pointer. The instruction says, after I'm executed, the result should go to this instruction. Each instruction can start executing, or start being fetched when all of its operands are received. Right. So it's completely data flow. Now, the implication is that potentially many instructions can naturally execute at the same time, right? Because one instruction can enable many instructions, right? And once you enable many instructions, those can enable many other instructions, right? It's inherently parallel. There's no sequentiality in this. That's the upside of this. Well, downsides we'll see. But let's take a look at what's the difference between these two. Consider a von Neumann program that looks like this, right? Eventually compute some value. It looks nice, right? We can all reason about it nicely. Let's build a data flow graph for this. Well, I'll answer those questions later, actually. But the data flow graph for this looks like this, actually. What you're really doing is computing z in the end based on some transformations that happen to a and b. And a data flow graph, this is a data flow node, if you will. You add a to b, and you generate a result. Now, data flow says once this instruction executes, its result should be sent to this node and this node. Actually, the left operand of this node and the left operand of this node. And once this instruction executes, its result should be sent to the right operand of this node and the right operand of this node. And when a node has both of its operands ready, which means both of these instructions have sent their result, this node fires, and after it executes, it sends its result to the left operand of this node. And once this node fires, it sends its result to the right operand of this node. And this node fires after both of the results in its input nodes are ready and computes its output. That's the data flow, right? No instruction pointer. Here, you need to go through the instruction pointer. Here, the significance of the program order is just as a convenience to the programmer, right? Here, you really don't need program order here, right? It really doesn't matter if you execute this minus first or plus first, or subtraction on addition first. Make sense? I'd encourage you to program with data flow. You cannot find computers like this today, but maybe good to re-examine. The other thing is, what is the significance of the storage locations? If you look at the storage locations, they're really just for locations to communicate values, right? What is the function of v and w? Well, v and w really don't need to exist, right? You're not using them, we're using them. They're not live out, assuming they're not live out from this. They're really to communicate values between different instructions. So storage, you can think of it as a medium for communication between instructions. And that's actually a very powerful abstraction now. Maybe you can get rid of some of the storage. If you don't need to store v, w, x, and y, well, you've got rid of a lot of your storage right here. And data flow, you've gotten rid of your storage. Well, it needs to be existent somewhere else, but we'll discuss that later on. But that's the difference between sequential and data flow. In data flow, you can actually program this way. So which model is more natural to you as a programmer? Up high. OK. That's about half of the class. Who says data flow is more natural? Who says, I don't know, both of them are natural? Both of them?
Well, it depends on the problem, right?
OK. That's a good point, actually. It depends on the problem, probably. Does it depend? Yeah.
Well, I would say it depends on who you are. Because as a programmer, I'm used to programming a sequential program. So that's natural to me. But maybe I have a problem that is naturally works in data flow. So.
That's actually also right, I think. It depends on not only the problem, but who you are, too. And perhaps your background. If you had always been programming with data flow, maybe that would be more natural to you, right? But we've been programming this way. At least I have been programming this way. So this is actually a good question to ask. I think, I may think that sequential is more natural to human beings. Human beings tend to be sequential in general. Is that true? Who agrees with that? OK, we have some agreement. Who disagrees? We're not sequential in nature. OK, that's good. You're not in the majority, unfortunately. No, that's good. I think this is actually a good question. People have proposed data flow model to be exposed to the program, and it hasn't been successful in the past. This model has been extremely successful. And it's not clear if that's because naturally as human beings we're sequential, or it's because of the education. This is a nature versus nurture debate, right? That's very relevant in psychology. But for whatever reason, sequential is more natural to people, and this is for most people, I should say. That's why this paradigm has been very successful at the programming level. Now, that doesn't mean that this cannot be successful, but it requires some more work to become more natural. I think it's similar to here and here. It's much more difficult for people to program multi-core processors, to write multi-thread programs as opposed to single-threaded programs. Except this is a different model. Anyway, this is something to think about. But the point is that your ISA does not need to be sequential. You can design a completely different computing system. And actually, let's look at a data flow machine. In a data flow machine, the program actually consists of this data flow graphs. And a data flow node fires when all of its inputs are ready, when all of its inputs have tokens. And this looks like, this could be your instruction representation, right? No program counter, but basically you have, this is your opcode. This is whether or not your left operand is ready. This is whether or not your right operand is ready. This is the value of your left operand. This is the value of your right operand whenever you receive it. And this is the destination of your result. Basically, in linear, in a memory location, this tells you which instructions to fetch next. This is encoding that you will use. Now you can actually build a complete program this way. Now it's easy to imagine pluses and minuses, but you could actually do conditional operations, right? So let's take a look at it. This is a branch operation. The idea is this is the Boolean input, control input. If it's true, then it passes the input. It fires when both of its inputs are ready. This is the data input. This is the control input. If the control input is true, it passes the data input to the true path. And if the control input is false, it passes the data input to the false path. Right? This is how you can do branching. You could do relational. You could do comparisons. You could generate the control input to conditionals using relationals. This is an example, right? This is greater than. It basically compares left operand to the right operand. It fires when both operands are ready, both tokens arrive. And in this case, it generates a true. 10 is greater than 7. It generates a true, right? If it was 7, 10, it would generate a false. This barrier synchronization. How many of you know about barrier synchronization? Some. So the idea of a barrier synchronization is actually coming from parallel programming. But basically, you have a program, and you've divided into multiple threads, if you will. And each thread does something, but then eventually they need to synchronize at the end, right? So this is, let's say, thread 0, thread 1, thread 2, thread 3. Well, I guess I have thread 4, 5 threads. You parallelize this portion. This portion is parallel. And at the end, the threads need to communicate with each other. How do they communicate with each other? Well, how do they know they should start communicating with each other? Well, you basically add a barrier to your program. And what is a barrier? It could be a shared memory location that says how many threads have actually arrived to that location at that point. Right? Whenever a thread finishes its work, it just increments the barrier or decrements the barrier. Right? And when all threads finish their works, they have all decremented the barrier, and the barrier has become 0. At that point, the computation that comes afterwards can resume. Right? This is a way to do synchronization in parallel programs. Let me give you one example. Even though I will diverge, I think it's important to give this example. So why would you do this, for example? Let's say you're counting the number of A's, B's, C's, D's, the letters in a book. Right? One way to parallelize this is, let's say your book is 5 pages. Right? You divide the work. You take page 0 here, and you give it to a thread that counts the letters in page 0. You take page 1, and you give it to the same thread. It's the same piece of code, but it operates on this data on page 1. And so on, right? You have 5 threads operating on 5 different pages. And eventually, at the end, they generate a histogram of the count of letters in their respective pages. Now, what do? You want the count of letters in the entire book. Well, at this point, you may have another thread that basically takes and sums up those histograms. Right? But this thread cannot start work in the strictest way of writing this program until all of these threads finish. Right? Otherwise, you may get an inconsistent histogram. Right? That's why before you start add up histograms thread, you'd better finish all of those threads that are counting their own pages. So that's a very powerful way of doing parallel programs. And this is one example. You could actually implement this in Dataflow. Yes?
So I see why you would need to have a barrier synchronization in a von Neumann machine, but I don't see a need for that in the Dataflow machine. Because you wouldn't have all the data. You would have to wait for all of them to do the next computation.
That's right. So that's a good question, actually. It turns out not all of the things that we want to do are perfectly doable in Dataflow. For example, if you want to do a bank transaction, you really want everyone to wait for something before you start the bank transaction. And this has been the Achilles heel of Dataflow. How do you do a transactional computation? You really want to execute only one thing, have only one thing execute that transaction. There may be a better way, there may be another way of implementing it, but people have banged their heads quite a bit on the wall and couldn't find easy ways to program this. Does that answer your question? Yeah. Basically, you want all threads to complete, all data values to arrive before you start the next computation. So you could implement this as a Dataflow node. OK. I think I'll take a break by asking you what this program does. Well, we're late, but that's OK. So here's an example Dataflow program. You can take a bio break, certainly, but you can also look at the program. My question is, what does this program do? I guess I'll be a little bit more clear here. So here, the initial value is 1. Here, the initial value is n. These are the two inputs to the program. This is the output of the program. And you have a copy node which copies the value to both of its inputs, both of its outputs. You've seen the relational. Basically, if the input is greater than 0, it basically generates a true, otherwise false. Copy, again, copies. You have a branch node. This means that the value just dies. It doesn't get forwarded anywhere. There's a multiply, copy, decrement, branch. And this thing, actually, it should really be a Dataflow node over here. This is a merge. Basically, it either takes the value that's present over here or the value that's present over here. Basically, if a value comes from here, the value goes down here. Similarly to this n. Initially, it's n, but later on, it'll be something else. Should I give you 5 minutes to figure out what this program does? All right, let's do it for 5 minutes. In the meantime, you can take a bio break too if you don't want to solve the Dataflow program. So in the meantime, I'll stop our recording for a while. There you go. So I'll take a break while you're solving it. Excuse me. Let's see. Oh, I see. Well, I think it's a matter of notation in this case. Yeah. Well, it really depends. You could potentially have multiple destinations. For example, if your instruction encoding allows, this decrement may have multiple destinations. If one of your, well, I guess you could have it in the copy node, or you could have it in the decrement itself. Right. Okay. So basically, what is the trade-off that we're getting at here? Let me make sure that this is recording, by the way. Yes, it is. The trade-off we're getting at is, do we actually need an instruction pointer in the ISA, right? This trade-off, or this question, the answer to this question determines whether you have a control-driven sequential execution of von Neumann ISA, where the instruction is executed when the IP points to it, and IP automatically changes sequentially. If the answer you give to this is no, then you get data-driven parallel execution. Actually, you could have other models too, but let's assume that these are the two things. An instruction is executed when all of its operand values are available. And this actually caused many, many trade-offs. I'm not going to be able to cover all of this. You'll see this in the Dataflow lecture when we get to it. But there are many high-level trade-offs, right? Now, what is the ease of programming for average programmers? It actually becomes difficult with data-driven programming. Because if your instructions are that way, then you need to really fit your problem such that it's data flow. Right? It may be easy for some problems, but it may be difficult for some other problems. It's a lot easier to say, I'm going to execute this instruction first, this instruction next. Ease of compilation also becomes difficult in this case. In fact, people have developed special languages for data flow when people were designing data flow machines. Which one has better performance? Well, it's likely that this is inherently more parallel, right? But people have actually developed, by exploiting the difference between the layer between ISA and microarchitecture, at the microarchitecture level, people have designed machines that do data-driven execution. In fact, all of the machines that you're using today, the out-of-order execution machines, the way they operate is, at the architectural level, as exposed to the programmer, they have the von Neumann model. They're control-driven. At the microarchitecture level, under the hood, they all employ principles of data flow execution. The instructions actually get executed when their operands are ready. But this is all hidden from the programmer, so that the programmer doesn't need to deal with it. Goal is to get more performance. That's the principle of out-of-order execution. Actually, you've seen kind of out-of-order execution's principles. What out-of-order execution does is takes instructions that are written in sequential order, buffers them in a buffer, and extracts the data flow of those instructions. And instructions get executed when their operands are ready. And eventually, when the results are being reported to the programmer, they're reordered, such that they obey the program order. Programmer sees nothing. No data flow happening underneath. That's the beauty of the distinction between architecture and microarchitecture, right? The idea is it's easy for the programmer to program. You have a control-driven ISA, but data-driven happens underneath. Which one's more complex? Well, if you really obey the von Neumann model without doing out-of-order execution, then that's probably simpler, right? Data flow is actually a lot more complex, as we will see when we talk about out-of-order execution. OK, so there are many high-level trade-offs. There are many other ones also that I'm not going to go into over here. Actually, with ease of programming, let me tell one thing, because we're going to talk about this later on. If you have data-driven execution at the ISA level, what is exposed to the programmer is data-driven. The programmer has no idea when you stop a program. The programmer has no idea of what's the architectural state. Right? With a control-driven program, you have the program counter. When you stop the program, you're guaranteed that the instruction that the program counter is pointing to has not executed yet, and everything else has completed before, and nothing after that has executed. So it's a very clean state. That's the idea of a precise state. We'll talk about precise exceptions later on. With control-driven execution, you can have a precise state very easily. With data flow, it's very difficult, right? Because you have this huge data flow graph, and it's not clear when you stop the program which instructions have executed and which instructions have not executed yet. It's a huge amount of state. Even if you expose that to the programmer, now the programmer needs to figure out, oh, this instruction has executed, this instruction has not. How do you debug that program? Right? It's very difficult. With sequential programming, it's a lot easier. Say, oh, this instruction, I'm at this point, now I can go back and figure out what mistake I made in my program. OK, we'll get to that also. OK, we've talked about the ISA level trade-off, but I've actually foreshadowed this. A similar trade-off, control versus data-driven execution, can be made at the microarchitecture level as well, instead of changing the ISA. So what's the difference between ISA and microarchitecture? Again, ISA specifies how the programmer sees instructions to be executed. It's the hardware-software interface. Microarchitecture, how the underlying implementation actually executes the instructions. So ISA may be sequential. Programmer may see a sequential control flow execution order, or it could be data flow. Microarchitecture underneath is totally independent. It could be sequential or data flow. You could actually have 4 components. You could take the Cartesian product of control-driven versus data flow at the ISA level and control-driven versus data flow at the microarchitecture level, and you could have 4 different ways of designing a computer. Well, I guess data flow at the ISA level and control-driven, sequential at the microarchitecture level is probably not a good idea, right? You made life hard for the programmer such that you're not going to exploit it. Right. So microarchitecture basically can execute instructions in any order as long as it obeys the semantics specified by the ISA when making the instruction and results visible to the software. That's the beauty of doing things in the microarchitecture. As long as you don't change what the programmer sees, you're golden. You can do anything you want. This is the key. It should obey the contract. Programmer should see the order specified by the ISA. So we'll get back to the von Neumann model, but if you want to learn more about data flow, this is one of the first papers that introduced it in ISCA. ISCA is a top conference in computer architecture, one of the top conferences, international symposium. And people have actually implemented a lot of data flow computers over the years. And they have not been very successful because it was very difficult to write software for them. It was very difficult to debug them at the ISA level. What has been extremely successful is data flow at the microarchitecture level. At the ISA level, you keep control flow. At the microarchitecture level, you do data flow-like execution, out-of-order execution. But we'll talk about this later on, data flow itself later on. But if you're really impatient, you can look at the lectures from 740, even for 447, but 740 lectures are more comprehensive. Okay, the von Neumann model. Basically, all major instruction set architectures today use this model. x86, ARM, everything that you see or do not see anymore. I guess alpha doesn't exist anymore, right? Alpha is a beautiful ISA, but unfortunately, doesn't exist. Well, it exists, but it doesn't. Are there alpha computers? Has anyone heard of alpha? Let me ask that question first. 1, 2. That's it? Wow, am I that old? I'll make you read an alpha paper, probably. Okay, so but underneath, as I said, at the microarchitecture level, the execution model of almost all implementations or microarchitectures is very different. And what are the differences? We'll cover all of these differences, actually. We'll first focus on ISA starting today, but we'll cover the microarchitecture a lot in this course. They all do pipeline instruction execution. They pipeline the instructions. When one instruction is being executed in the execute unit, another instruction is being fetched. Another instruction is being decoded. Another instruction is accessing memory. This is pipelining, right? You pipeline the execution. You break the instruction processing into multiple stages, and in each stage, you can have a different instruction. Now, even this does not obey the von Neumann model, right? The von Neumann model says you cannot start an instruction, you cannot fetch an instruction before the previous one is complete. Even pipelining disobeys that. So microarchitecture is different from the instruction set architecture's principles. But it obeys what should be reported to the software. So Intel 486, for example, was pipelined. Multiple instructions at a time. Intel Pentium, for example, had 2 instructions at a time. It could fetch, decode, execute 2 instructions at a time in parallel. This is called superscalar execution. And we'll see that also. Even that also disobeys, right, the von Neumann architecture. Out-of-order execution with Pentium Pro. This is examples from x86 architecture. There were other out-of-order machines. But Pentium Pro was one of the first general-purpose machines that did out-of-order execution. Underneath, instructions were executed out-of-order in data flow fashion. If you look at the stored program concept, separate instruction and data caches kind of disobeys the von Neumann model also, right? In today's machines, you have separate instruction cache and separate data cache. They're not unified, at least at the level closest to the processor. So you can do many, many things underneath without exposing them to the programmer. Okay, what happens underneath is not exposed. What happens underneath that is not consistent with the von Neumann model is not exposed to software. That's the difference between ISA and microarchitecture. You can have many different implementations underneath that still obey the same instruction set architecture. So this is actually what I showed you earlier. I'm not going to go over this again, but this is the architecture definition that we're going to use in this course. It's ISA plus implementation. But the traditional ISA definition, remember Gene Amdahl with his picture in the, I guess, the air-cooled LSI, 300-gate LSI logic. Basically, he defined the term architecture to describe the attributes of the system as seen by the programmer. as opposed to, as distinct from, the organization of the data flow and controls, the logic design, and the physical implementation. This is the traditional definition. So when I talk about ISA, this is the ISA. This is the ISA. This is the microarchitecture. OK. I guess without harping on it, this is what the software and compiler assumes and hardware promises, what the software writer needs to know to write and debug system and user programs. This is a good rule of thumb. Microarchitecture is a specific implementation of an ISA. So when we talk about microprocessor, what is that? That's basically all of it. You can think of it as ISA and microarchitecture plus circuits, right? And a loose definition of architecture is really ISA plus microarchitecture. So let's take a look at an example. Actually, this exists in real life. This is really an interface, right? When you drive a car, you have a certain interface. But the underlying implementation can be very different. You press the gas pedal, you assume the car will accelerate, right? That's the interface. That's what the interface promises to you, and hopefully the underlying implementation somehow delivers it. You don't care about how it delivers it. Well, maybe you do care about it. Maybe you're a car enthusiast. Maybe you do care about the specifics, but the average user doesn't really care about how how pressing the gas pedal enables the acceleration. Right? Internals of the engine or internals of the car actually implement the acceleration. Right? And implementation can be various as long as it satisfies the specification. For example, add instruction versus add implementation. Even that's a choice, right? An add instruction, you just care about the add is done, right? There's some specification of the add. It takes two operands and adds them and puts the result back in register X, let's say. But you could implement at the lower level in many different ways. You've seen adders before, right? In 240, I assume. You've seen the ripple carry adder, carry look ahead, and other adders too, perhaps. How about the bit serial adder? Yep. Yes or no? Who says yes? They've seen it. That was in 240? Who says no? That was not in some 240s, maybe. Or maybe. I'll tell you what it is. It's fun. Well, maybe it wasn't interesting. That's why you don't remember it. It's actually interesting. But basically, if you think of a ripple carry adder, you add multiple bits in parallel, right? And you ripple the carry. So eventually, the carry chain is your critical path, right, in terms of the computation. And carry look ahead tries to parallelize that carry computation, at least minimize the delay. Ripple carry doesn't deal with all that. It says, I'm going to add 1 bit per cycle. That's it. It's a very simple adder. If I'm going to add 32 bits, I'm going to take 32 cycles. Basically, instead of having 32 adders, full adders, you have 1 full adder, and you operate it over 32 cycles. Does that make sense? You add the first bit. Well, I guess if you think of the adder like this, as a 1-bit adder, if you have ripple carry, it looks something like this, right? If you have a 4-bit adder, it looks like this. You have the carry in, B0 coming in, and then you have the carry out, and then the result, right? And this is your carry chain, if you will. And this is your A3, B3. And then you have the carry out, and then this is your output out of the adder. And think of this as 1-bit adders. Here you still have a 1-bit adder, but it looks like this. You have the inputs, and you have the output, and you have the carry out. And you can have a carry in, of course, but let's assume that there is no carry in. So what you do is, well, you have a carry in input also. What you do is you latch the output and you latch the carry out such that in the next cycle you recycle, right? You recycle the carry in. And then in the next cycle, your next inputs come. Instead of A0, B0, when you cycle the clock, A1, B1 comes, and you take the carry out coming from the adder. And then you, of course, have, again, 4 bits. You shift the bits. Make sense? It's a 1-bit adder that's cycled 32 times to get a 32-bit result. Well, in this case, it's a 4-bit result. It's beautiful, right? Simple. The hardware cost is really small. Do you want to implement this in your microprocessor? Yeah? Probably not. Well, it depends. Again, it depends on your design point. Right? In today's processors, this doesn't get used. because you want the add to be as fast as possible. In fact, in Pentium 4, for example, the add took 3 cycles, but it was pipelined. You could actually do 3 adds per cycle. In fact, you could do 6 adds per cycle in Pentium 4 because they had a mode where you could operate the adder at twice the frequency. They called this the fireball. Yeah, you could operate the adder at twice the frequency as the rest of the pipeline. So you could do 6 adds per cycle at throughput. If they did it bit serially, you could potentially still do 6 adds per cycle because that's throughput, right? But the latency would be much higher, right? If you could pipeline this bit serial adder, right? Maybe, maybe not. Maybe you cannot pipeline it below that. So that's the downside. Yeah, if your latency is much higher with the bit serial ladder. Why would you ever want to use this? Yes.
Reduce logic space.
That's right. Yes. If you don't care about latency, for example, I mean, you certainly reduce the logic space. That's the upside. And if you don't care about latency, it may be a good trade-off. There was a machine called the connection machine. They executed the scientific applications, very large-scale array computations. Think about nuclear power computations, let's say. And they had lots of parallelism. They had lots of adds, which means that each add doesn't need to be long, as long as you can do many, many adds in parallel, right? You didn't care about the latency of a single add. You cared about the latency of doing 1 billion adds, let's say, maybe 1 trillion adds, right? In that case, the latency of a single add doesn't really matter, right? That affects perhaps a little bit a few number of cycles at the tail. In that, 4K adders, and each of the adders was a bit serial adder, and their latency was 16 cycles for each add, but they could do 64K adds in parallel. This is the connection machine. So for their design point, the bit serial adder was a much better design choice because they didn't need to design a complex adder. It's very simple. The hardware cost is much lower, but they could pack 64,000 of them. So it really depends on your design point. If you have that kind of parallelism, maybe it's okay to have a bit serial adder. Maybe in today's GPUs, it may be okay to have a bit serial adder if you have lots of computation, right? If you have image processing and you're processing huge images, maybe you don't really care about the latency of a single pixel. Right? Now, today's GPUs don't have bit serial adders, as far as I know, but you could. 86 ISA has many implementations also, 286, 386, 486, Pentium Pro, Pentium 4 Core, and I haven't kept up with it after that. And x86 ISA has also evolved, but the core x86 has not changed. The other thing is microarchitecture actually changes faster than ISAs. This is usually the case. So there are very few ISAs, and in fact, they're getting fewer and fewer. For example, alpha doesn't exist anymore over here. But there are many microarchitectures. Why do you think this is the case? Yes?
You can change the microarchitecture without breaking software compatibility.
Absolutely, yes. If you want to change the ISA, you're actually affecting everybody else above, the entire software. Right? Whereas if you want to change the microarchitecture, it's simple, right? The same software will run. Basically, you're not affecting compatibility. You're not affecting backward compatibility, if you will. Well, you can change the ISA without affecting backward compatibility. Backward compatibility is, will the same software that you have run in this generation of the machine that you're now designing, changing the ISA for? Basically, this guarantees that you run software that you've designed that was designed previously. You can change the ISA without affecting backward compatibility as long as the new ISA is a superset of the previous ISA. Right? And that's been one of the curses of the x86. x86 has been very powerful because it has this huge software base and because they have been very careful not to break backward compatibility. That's why x86 has added a lot of kludge, because there's lots of instructions that are not used today except for this little piece of software that was written perhaps in 1980s that is very critical because nobody wants to change that software. Right? Maybe nobody understands it at this point. Right? So that's the importance of software. Software is very complex. Okay, So what is ISA? This is an old version of the Intel architecture manual. But ISA consists of many different things. It's not just instructions, even though it's called the instruction set architecture. It's really the interface between the software and the hardware, what the programmer or the system programmer needs to know. And we'll cover instructions a lot later. And you'll actually implement condition codes with ARM this time. It consists of the memory, what is address space, addressability, alignment, virtual memory management. We'll cover that. But it does consist of other things that I'll briefly want to talk about very quickly so that you know, actually, these are part of the ISA. Call, interrupt, and exception handling. We'll cover that. Access control, priority privilege. We'll cover that in virtual memory. I/O. How do you perform I/O? Input, output. That's part of the ISA. How do you perform task or thread management? Well, the multi-core processor is gone here, but how do you perform that? Again, is part of the ISA. Power and thermal management. Increasingly, energy is more important in the design, and these are first-class primitives now in the interface to a microprocessor. How do you change the voltage and frequency of a processor? Well, you need some instructions or some support. Multi-threading, multiprocessor support. These are all parts of the ISA. Actually, volume 3. I'm not sure. It's still volume 3, right? Yes? Volume 3 of the Intel ISA, x86 ISA, talks about all of these system architecture functions. It's a great thing to read, especially if you're interested in the system interface to the processor. So microarchitecture is the implementation of the ISA under specific design constraints and goals. Does anything done in hardware without exposure to software? Let's try to look at some of these things. Because actually the definition of this depends on what the ISA is, right? Pipelining, for example, is done in microarchitecture traditionally. But we'll see cases where this is actually exposed to the ISA also. We'll talk about very long instruction word architectures that try to expose part of the pipeline to the ISA. In-order versus out-of-order instruction execution, that's done in the microarchitecture. Memory access scheduling policy that we discussed last time, right? That's done in the microarchitecture also. That's you don't program knowing that, right? Or you don't configure that. But again, going forward, maybe this should be part of the ISA, right? Maybe programs should say, oh, you should use this policy. Maybe they can modify this policy, the system perhaps, the system program. Speculative execution, we'll talk a lot about speculative execution. This is, speculative means, execution means doing something before you need it, before you know that you need it. That's done underneath. Existing processors predict a lot of things. They predict the access pattern. They say, oh, this program is probably going to access this memory location, so let me grab it and place it into the cache. That's speculative, right? That is not part of the ISA. Superscalar processing, multiple instructions at a time. Superscalar processors do that dynamically, purely in hardware, purely in the microarchitecture. So that's, again, part of the microarchitecture. But we'll see another paradigm called VLIW, as I said, a very long instruction word, where the ISA enables the software to specify which instructions can be executed in parallel. And the software packs multiple instructions in a single instruction word, if you will, a long instruction word. And the hardware knows that all of the instructions that are packed in this instruction word can be executed in parallel. That's nice, right? You can do multiple instructions. Actually, some embedded ISAs, some of the TI processors have this kind of ISAs. Very long instruction word. Clock gating. Gating, so if you're not using an adder, for example, you can gate the clock to it such that it doesn't consume dynamic power. You can even gate the power to it such that it doesn't consume dynamic or static power. So that's done in the microarchitecture. You could potentially expose this to the ISA as well, right? You could say the programmer can gate a block, maybe not an individual adder, that may be a lot of overhead. But the programmer, let's say, they know that they're not going to use the floating point unit. They can say, turn off the floating point unit for the rest of this program. It's not done today. Caching. We talked about caches briefly last time. Well, you're going to be sick of caches at some point in this lecture, probably. Well, hopefully not sick of caches, but you're going to know a lot about caches. This is all done in the microarchitecture today. How many levels? What's the size? What's the associativity? What's the replacement policy? Right. Well, it's not actually perfect because in today's ISA, there are instructions, as I mentioned last time, I believe, that's the programmer can use such that they can say this load is loading data that's not going to be reused again. Right? It's called a non-temporal load. In fact, x86 ISA has that. Now you can specify the behavior of caches a little bit. Not the entire behavior, but some behavior. Prefetching, we just talked about this. Voltage and frequency scaling. Is it part of the ISA or is it part of the microarchitecture? Now increasingly it's part of the ISA actually. Earlier processors used to do voltage and frequency scaling underneath, but now it's being exposed to the software. Error correction. It could be part of the microarchitecture. Today errors are corrected in caches, especially large caches. You need to pack a lot of cells onto the chip. As a result, these caches, the charge that's stored in the caches becomes small, so they're very prone to errors. So there are error correcting codes that are used in many processors, large caches. And these are being corrected during dynamic operation. And this is not being exposed to the user. That's part of the microarchitecture, right? Okay. I guess this is an exercise. Maybe this is a good place to finish. Well, I guess let's go through it. I'll cover the entire time. So add instructions opcode. Is that part of the ISA? Yes, right? This is an opcode. It must be visible to the software. Somebody's generating that opcode. Number of general purpose registers. Is that part of the ISA? Yes. The compiler needs to know it, right? Otherwise, how is it going to allocate registers, right? That's a fabulous problem, by the way, register allocation, how you do it in compilers. Have you guys taken any compilers course? Oh, you have? Oh, cool. You study the register allocation problem? It's fun, right? Oh, the graph coloring, and it's tough. It's a very tough area right now, but it's a lot of fun. But somebody needs to know that. Number of ports to the register file. That's not part of the ISA, right? At least not in traditional ISAs. You could have many, many ports to the register file without exposing to the programmer. Number of cycles to execute the multiply instruction. Is that part of the ISA? It's a tough one. Depends. Traditionally, it's not part of the ISA, actually. In x86, for example, it's not part of the ISA. The number of cycles, it depends on the implementation. But for some ISAs, like very long instruction word ISAs, this is exposed to the programmer such that the programmer can schedule the instructions. Now, this can, if you know this can aid your program such that you can do a better job scheduling instructions, right? If your multiply takes 2 cycles, you can put the instruction that's dependent on the multiply after 2 instructions, let's say. This, you can optimize your program. But this doesn't mean that that's part of the ISA. You don't have to do that, right? This is just an optimization. So a lot of the optimization manuals tell you how long it takes to do the multiply, but this is not the specification. This specification can change without changing the interface. Whether or not the machine employs pipeline instruction execution. No, not part of the ISA, again, right? Actually, all of these can be part of the ISA as long as you expose the program. Again, this is interface, right? Somebody designs that interface. You can make all of these part of the ISA or none of these part of the ISA. Well, some of them may be difficult unless you don't have an add instruction. Unless you don't deal with registers. Actually, registers do not have to be part of the ISA again, right? If you have purely memory-to-memory machine, which is part of your homework we'll deal with, you don't need to have any registers. That doesn't need to be part of your ISA. Okay. So microarchitecture is the implementation of the ISA under specific design constraints and goals. I think I'll stop here. We'll pick up with design points. And I guess I'll see you Friday. We'll have class on Friday. And hopefully, we'll have a better classroom.
Is there a recitation this week?
There are recitations this week. I forgot to mention that. And there are ARM ISA tutorials that are given by the TAs during the recitations.